So you should have already tried the problems, the 6 sample questions. We're going to go through and correct them and help connect the dots and help you kind of understand the IB language before taking our first real actual IB test. Alright, so first thing I want to point out about this question is that it says that we do have a gas. So if we have a gas, we know a couple of things. We know gases have particles that are moving very fast, and that because of that, those particles are very small apart. So that comes from kinetic molecular theory. So kinetic means particles are moving, motion. Molecules tell me what the particles are. We have moving molecules. And theories explain, whereas laws would just state an observation, theories will explain the concept behind it. So using the explanation of molecules, we can talk about how the speed of the particle will affect the time. So if we know gases are typically at a higher temperature, then we know that they would have a higher kinetic energy. That comes from the second postulate of KMT. We also talked a little bit about the formula for kinetic energy, which is 1/2 mv squared. And while you don't have to have that memorized, you should know that kinetic energy is not directly or linearly, but proportional to the velocity. Basically, if I increase the kinetic energy, I increase the velocity. So the bottom line in here is those particles are moving fast. So if they move fast, that takes very little time. So the second part of this question actually asks us to explain the connection between time and temperature. So we already talked about how if we have the higher temperature, we have a higher kinetic energy and therefore a higher velocity. But what is velocity? Velocity is how far something goes in a period of time. So if I increase the velocity, that takes less time. Basically, the point you need to make is that velocity and time are inversely related. So if it is going faster because it's at a higher temperature, that would take less time. So for an empirical formula question, the steps are to go from percent to gram, from gram to mole, and then to divide by the smallest. And that's going to give us our ratio. So for the percent to gram part, it doesn't matter what the total mass is. The percentages are going to give us the same proportion. So why not just pick 100 grams to make this easy? So that'll give me 85.6 grams, 85.6% of 100 for carbon, and 14.4 grams for the hydrogen. But we can't compare gram to gram, so our first step is to convert to moles. So 1 mole on top. The molar mass of carbon is 12.01 grams. For hydrogen, the molar mass is 1.01. And so for carbon, that is 7.13. And for hydrogen, that is 14.3. So that's how many moles I have. So then we're going to divide by the smallest, which of the two is 7.13. So this is, of course, 1. And then 14 divided by 7 is 2. So that tells me I have 2 hydrogens for every 1 carbon. So the empirical formula is CH2. So for this question, I'm going to focus on what it's asking for because it's giving me a whole lot of numbers. But if I focus on what it's asking for, it can help me figure out what I need them for. So molar mass, or m sub r, relative atomic mass, is always grams per mole. So from the question, it does tell me how many grams I have, 1 gram, but it doesn't tell me how many moles. So I'm going to need to find that. Best way to find that? PV equals nRT, which is why it's giving you temperatures, pressures, and volumes. So using PV equals nRT, I can start plugging some things in. For pressure, I have pascals and ATM given. I also have decimeters cubed for the volume. So I've got to think first, what kind of R do I want to use? And the one that makes the most sense to me is the 8.31 kPa over mole liter, or I'm sorry, mole Kelvin. So that means I need to get the pascals into kilopascals, which is just dimensional analysis. So 1.01 times 10 to the 5th Pa. Then I would have 1 kilopascal on top, 1,000 kilopascals on the bottom. And so basically I have 101 kilopascals. So I'm going to plug that in for P. So the R that I chose also used liters, so we should know by now that decimeters cubed and liters are the same thing, so I'm just going to plug it in as liters. We're solving for N. We're going to use the R, and then they're nice this time and went ahead and gave me the temperature in Kelvin, but do watch for that. So if I take my 101 kilopascals times my 0.399 liters, divide that by the R, and divide that by the 273 Kelvin, I get that N is 0.0178. That's not the final answer. Why did I need that again? I need to plug into 1 gram divided by the number of moles. So m sub r is the 1 gram on top and the 0.0178 moles on the bottom, which gets you 56.8 grams per mole. So technically the 1 gram here would limit this to 1 sig fig, so this would round, if this were your final answer, to 60 grams per mole. And honestly, IB would probably put that as 6 times 10 to the first power. But the sig figs kind of mess up the next part. So I'm going to stick with the 56 for now. So this is much neater. I kind of was running out of room here, so I just wanted to go over it again. We're using PV equals nRT to solve for the N. So we plugged in, we changed this 101 pascals to 101 kilopascals. Decimeters, liters, same thing. So that's kind of all wrapped up into what they're calling a joule. kPa liters, decimeter cube, same thing as a liter. And then the Kelvin. So to find N, you're taking your PV, dividing it by R and T to get N. So then we get the number of moles to plug into the bottom of your grams per mole. And so they have their answer actually left as 3 sig figs as well, even though the 1 gram would actually make it 1 sig fig. But when we do the next step, we're going to need a more complete number, for lack of a better term, so we're going to use the 56. So in order to find the molecular formula, I just found the molar mass of that molecular formula, but now I need to find the molar mass of the empirical formula. So I'm just going to take the 12.01 and add that up with 1.01 twice, and I get 14.03. So if I know that the total molar mass was 56, and I know the empirical molar mass is 14, that gives me a multiplying factor of 4. So I'm just kind of rounding these molar masses. That's why I'm using 56 instead of 60, because I'm trying to get an even number. I shouldn't say even, a whole number to be my multiplying factor. So we're kind of giving a little leeway to the numbers there. So I've got CH2 times 4, which would give me C4H8 for the final answer. So they do the molar mass of the empirical just like we did, but then notice in their explanation to get up to the multiplying factor, they also say about. So don't overthink the sig figs. So we just want to figure out the relationship between the empirical and the molecular formula. All right, so for this question, again, it gives me a lot of information. So I'm going to start with what do I need so I can figure out how to use the numbers. So I'm trying to calculate concentration. So what IB units do they like for concentration? And they even say it here. We want moles and we want decimeters cubed. So it just doesn't give us that exactly. It gives me grams of just sodium. I'm trying to find sodium hydroxide, so that's going to be a few conversions. And then for decimeters cubed, the only problem is that they gave us centimeters cubed, which shouldn't be a huge deal. All right, so I'm going to do the solute first. So I have sodium turning into sodium hydroxide. I know I start with 1.15 grams, but that's just of the sodium. So in order to convert one substance to another substance, I'm going to need to get to moles. So first I'll use sodium's molar mass, 22.99 grams to 1 mole. And then I'm going to use, since this was sodium, the mole ratio with sodium on the bottom, mole of Na. And I'm going to put the moles of sodium hydroxide on the top. And I want to keep it in moles, so I'm going to stop there and not go to grams. So the mole ratio, the coefficients here are 2 and 2. So we're just going to use the 2 to 2 ratio here. So if you do 1.15 divided by 22.99, the 2's essentially cancel out, and so you get 0.0500 moles, keeping with the 3 sig figs. So next I'll handle the volume. So we've got 250 centimeters cubed, but we want to get that to decimeters cubed. So we'll put centimeters cubed on the bottom, decimeters cubed on top. And you can go through meters like we've done in class, but at this point you know a decimeter is like a liter and a centimeter is like a milliliter, and there are 1,000 milliliters in a liter, so that's fine. You don't even really have to show this step if you can do it in your head. 0.25. Let me point out the sig figs here though. This is a hanging 0. So those are only 2 sig figs. So now we're down to 0.25 decimeters cubed. So then we would actually find the concentration. So the concentration is your moles per volume. So we're going to take the 0.0500 moles and divide that by the 0.25 decimeters cubed. And we get a final concentration of 0.20 mole dm to the -3. Final answer. So this is much neater, but I do want to point out the sig figs, 2 sig figs here, so this should be just 2 sig figs here. So the first step in this question is having us write an equation for hydrocarbon combustion. Notice that C2H4 is made of only carbon and hydrogen, so we call that a hydrocarbon. So C2H4. The fact that it is combustion tells us that it's reacting with oxygen. Also, you notice oxygen's mentioned in the problem a few times. And they do tell you it makes carbon dioxide and water, but that is something you should know. All hydrocarbon combustions produce carbon dioxide and water. All right, so to balance, I'm going to start with the carbons. That means I'm going to need 2 CO2s. Then I'm going to do the hydrogens. If I have 4 hydrogens on the left, I need 4 on the right, which would be 2 water molecules since they come in pairs. So that's 2 oxygens from the water plus 4 from the CO2 for a total of 6 oxygens. If I cut that in half, since I have diatomic oxygen, I need 3 molecules. So it's 1 to 3 to 2 to 2. Let me just point out the phases here. Hydrocarbons are typically gases. Think like propane, methane, natural gas, stuff like that. Oxygen, of course, you know is a gas. CO2, you know is a gas. And liquid at room temperature for water. That's going to be important. So this is an Avogadro's law problem. We've got to look at which one of the reactants and products are gases. We know that Avogadro's law is not going to apply to the liquid water over here. But we can get a mole ratio to help us figure out what volumes are equal to how many moles, because at the same temperature, this system, 1 mole of any gas should equal the same volume. So let's look at what volumes they gave us. For the ethane, or C2H4, we have 100 cubic centimeters. For the oxygen, we have 400. So it does tell you that there will be a volume of oxygen remaining. So that tells me that the C2H4 is my limiting reactant. You always have to think about what the limiting reactant is going to be, because that is what's going to kind of set your mole ratio. So how many moles of C2H4 do I have? Just 1. So that tells me that 1 mole of any gas is equal to 100 cubic centimeters. So in the end over here, if I have 2 moles of CO2, that should take up 200 cubic centimeters. So that's the answer to the first question. Calculate the volume of carbon dioxide. There would be 200 cubic centimeters. The volume of oxygen is a little bit trickier. First, we've got to figure out how much would be used. There is 3 times as much oxygen as there is ethane used for each reaction. So that means that every time I use 100 cubic centimeters of ethane, then I'm using 300 cubic centimeters of oxygen. So if I started with 400, but I used up 300, then I have 100 left. So at the end, I would have 100 cubic centimeters of oxygen left, because 300 would be consumed with the 100 butane. All right, so this is a more traditional limiting reactant problem. We're going to start off with writing a balanced equation. So zinc and iodide react. But the thing you have to remember is iodide is diatomic. Then when we combine our new molecule, zinc iodide, we have to consider the charges. Zinc is always a +2 and iodide is a -1. So when we crisscross, we get ZnI2 as our product. That 2 is coming from the crisscross, not from the diatomic iodide. So we have zinc plus diatomic iodide yields ZnI2. So, and notice the phases again here. So this is how you know it's not an Avogadro's law problem. It's going to have to be where you actually convert your grams to mole to find your limiting reactant. All right, so there is no shortcut for limiting reactant problems. We just have to convert both of them. So I'm going to start with my 100 grams of zinc. And we're going to convert that to moles. So the molar mass of zinc is 65.38 to 1 mole of the zinc. So I know moles of zinc will go on the bottom. And I am trying to convert to the zinc iodide to see how much product is formed. So the balanced equation, all of the coefficients were 1, so that part's easy, just 1 to 1. And then when we do this math, 100 divided by the 65.38, we get 1.530 moles of the zinc iodide. So then I'm going to also start with 100 grams of the I2. And so when I convert that to moles, I'm going to use the molar mass of diatomic iodide. Don't forget it's diatomic. This is a huge molar mass, 253.80 grams of I2. And then again with the mole ratio, yes, it's 1 to 1, but I'm still going to show it. So mole of I2 on the bottom and mole of ZnI2 on top, 1 to 1 ratio. So when I do 100 divided by 253, I get a much smaller number, 0.3940 moles of the ZnI2. So those are my two options. Basically, based on each one acting independently, I could produce either 1.5 moles or 0.39 moles. It's always the lower one. Once I have produced 0.39 moles, I am out of I2. How can I make ZnI2 if I have no more iodine? I can't. So I will never be able to make 1.5. I will only be able to make 0.3940. So that is the amount of zinc iodide in moles. And then the second part of this question is very specific. Which reactant is in excess? Now, most of the honors test actually asked you what the limiting reactant was. This is specifically asking the opposite. Based on this 0.394 being the lower number, I know that I2 is my limiting reactant, making zinc the answer to the second question, the one that will be an extra. Zn is the excess. Make sure that you answer the question that they ask. So the first part of this question just had us figure out how many moles of zinc iodide, and we decided on the 0.3940 moles. Now we just want to convert that to grams. So we're just going to use the molar mass. For zinc iodide, the molar mass is 319.18. So that gives a final actual mass of 125.8 grams of zinc iodide. This is definitely the hardest question of the 6. It's very confusing how much information they give you and when to use each one. So my best advice when this happens is to try to follow the parts. There's a reason why they break this down into 4 questions. They're trying to lead you to the answer. So just try to focus on answering like one question at a time and know that you won't use every part of the question in every section that we're answering. So throughout all 4, A through D, we'll end up using all of the numbers, but we're not going to use all the numbers in any one part. All right, so this first part, part A, asks you just to write the equation for a reaction between the acid, carbonate, producing salt and water. So it does tell you the type of acid that we're using in the question, the hydrochloric acid. So we know the formula for that is HCl. That's going to react with the carbonate. So this is part of the confusing part too. We have a carbonate given and it's wrapped up in a hydrate, but notice they didn't say hydrate, they just said carbonate. So I'm going to steal just the Na2CO3. And then that's going to produce a salt. So treating this like a double replacement reaction, kind of, I mean, only in the salt formation part, you're going to get the sodium and the chloride to combine together, the Na and the Cl. And then the H and the CO2 actually decompose after like bicarbonate breaks down. So that's going to then produce, and it does tell you, water and a carbon dioxide, H2O plus CO2. We are going to go over some standard reactions, things like carbonates break down and to produce carbon dioxide, and some rules like that, kind of similar to how carbon combustion always produces carbon dioxide and water. That's going to be part of one of the future units. So by the time you take your full IB test, this won't be such a confusing question. But for right now, we're kind of trying to guide you there with the hints of what's reacting and what's being produced. So then this is not balanced. To balance it, we would need 2 hydrochloric acids and 2 sodium chlorides. And that'll give us our final reaction that we can work with for the next part. All right, so this next question tells me, or next part of the question tells me I'm going to be looking at the neutralization. So I just want to look at the parts that are sodium carbonate and hydrochloric acid, and I only want to look at what would be used for a neutralization reaction. So neutralization calculations, we needed volumes and concentrations. We're going to use the volume and concentration to figure out moles, convert it, and figure out the concentration of the unknown. Think titration. So the part of the problem that I'm going to need right now is that I have 25 cubic centimeters of the solution neutralized by 48.8 cubic centimeters of hydrochloric acid with the concentration of 0.1 moles per decimeter cubed. So the one substance it does tell me is the hydrochloric acid. So I know that the volume of the acid is given here at 48.80 cubic centimeters. Since I know I'm looking for decimeters cubed, I'm just going to go ahead and convert this one. I showed that work earlier if you need to review it. So it's going to be 0.048880 decimeters cubed. Then the concentration of the acid they give is the moles per decimeter cubed with the acid. So it's going to be the 0.1000 mole DM-3. So they do give me this other volume. It just says of the solution. Well, what's the other substance involved here? Sodium carbonate. So do I necessarily think you should know off the top of your head sodium carbonate is a base? No, but the fact is it's being neutralized by hydrochloric acid. So is it a base? Of course. So, and again, I'm going to go ahead and convert this volume. 0.2500 decimeters cubed. So that's kind of my starting point. I'm going to start over here with the acids, where I can find the number of moles by multiplying the concentration times the volume. So the concentration is the 0.1000 mole per decimeter cubed, and I'm going to multiply that by the decimeters cubed. So if you don't necessarily have this molarity formula to the point that you can manipulate it off the top of your head like this, use your units. Decimeters cubed, we need to get it to cancel. So I'm going to multiply by decimeters cubed. Just make sure that you keep the like substances together. So I'm only working with the acid numbers right now. So then the number of moles for the acid is 0.004880. So basically we're just moving our decimal. So then the next thing that I need to do in order to be able to move over to the base side is to convert acid to base. So that's a mole ratio. So I'm going to take my 0.004888, I'm sorry, 4880. That wasn't decimeters, the decimeters canceled. Moles. That's of the acid. So I'm going to put mole of acid on the bottom, mole of base on the top. So if I go back to the balanced equation, which I don't have on the screen, from the previous slide, the moles of acid, there was 2 for the hydrochloric acid, and the sodium carbonate, there was just 1. So that's going back to the balanced equation from parts A. So basically I need half as many moles for the base. So it's going to be 0.002440 moles of the base. Then finally I can find the concentration of the base, which will be the moles per volume using IB units. So the moles, we just had 0.002440, and then we're going to divide that by the volume of the base that they gave us in the question, 0.02500 decimeters cubed. Sorry, I'm running out of room. So then the concentration of the base, when you divide that, is 0.976 mole dm -3 for the final answer. So just because it's so messy with me trying to write on the little screen, little slides, I just wanted to go over this again with the typed up. So we're using the volumes of the acid and base and the concentration of the acid. So starting with the acid numbers, we've got the concentration times the volume to get the moles of hydrochloric acid. And notice that they actually put it in scientific notation, which they tend to do when the numbers are even the slightest bit small. So if we've got this 1:2 ratio, we can use the mole ratio. This is from the first slide of 1 moles of sodium carbonate to 2 moles of hydrochloric acid, and that's going to give me how much of the sodium carbonate. So the units here would be moles of the Na2CO3. And then they did give the volume of the 25 cubic centimeters. They didn't show this work either, of converting this cubic centimeters to decimeters cubed. But that's where that comes from. So then we just take the moles, now that we've converted it to the moles of base, divide it by that volume, and we should get 0.076 moles decimeters cubed. And I think I did, yes. So this is all 4 sig figs. So I dropped a 0 myself on the last problem. So be careful of that. It should have 4 sig figs. So I think here's where it gets a little bit tricky. So I'm going to try to just focus in on the parts that I can handle one little bit at a time. So first I'm going to try to determine the mass of sodium carbonate neutralized. So we did find that in the last series of calculations. We just didn't have that as our final answer. In the end, we wanted concentration, but along the way, we found the moles of sodium carbonate. It was when we used the mole ratio. So it was 0.002440 moles of the Na2CO3. That was how many moles we divided by the volume. This time it's just asking for mass instead of a concentration. So we know how to go moles to mass. We're going to just divide, or in this case, multiply by the molar mass. So 1 mole on the bottom. And the molar mass of sodium carbonate is 105.99 grams. So that gives me 0.2586 grams. So that's my mass neutralized. But if you notice, now we're trying to figure out how much was present in 1 decimeter cubed. Well, we didn't divide by 1 decimeter cubed before, but that's okay. If I can figure out how many grams per that decimeter cubed, I can use a proportion to figure out how many grams for exactly 1 decimeter cubed. So I'm going to set up a proportion for this next part. 0.2586 grams, and that was for the given volume of the 25 was how much was used for neutralization. So in decimeters cubed, that would be 0.02500 decimeters cubed. So I'm trying to figure out how many grams if I just have exactly 1 decimeter cubed. So we're going to cross multiply here to solve for the grams, and we get 10.34 grams of Na2CO3 in 1 decimeter cubed solution. So they just set up the proportions slightly differently, but obviously you get the same answer. Instead of converting to decimeters cubed, they converted to centimeters, so that because they left the 25 given centimeters, and then they converted 1 decimeter cubed to 1,000 centimeters and got the same answer. Sloppy on the sig figs in the work, but they do have their 4 sig figs at the end. All right, so this mentions hydrated crystals. Finally, remember how that sodium carbonate was attached to some number of water molecules? Now we're going to do our hydration number calculation. So it does give me the total amount of hydrate. So it's going to be the 27.82 grams of hydrate. And typically to find the hydration number, we're going to need to compare anhydrate and water. So we know we can subtract out the grams of anhydrate, which would be your constant mass if you're doing the experiment. And then the mass that's left would have to be the water, since that's what leaves during dehydration. So if we look, the anhydrate is Na2CO3, and it's in 1 decimeter cubed of water. Well, we just found that in the answer to part C, how many grams of sodium carbonate would be in this 1 decimeter of water. That would be the 10.34. And if we find the difference there, the amount of water is 17.48 grams. So we want to find the comparison of how much anhydrate to water, but we can't compare grams. So of course we need to convert to moles. So I'll do the anhydrate first. 10.34 grams. 1 mole on top. Molar mass on bottom, which we used earlier, was 105.99 grams. And so that gives you 0.09760 moles. Then if we do the same thing for the water, 17.48 grams. 1 mole on top. Molar mass of water is 18.02. And so then it's 0.9698 moles. So to compare them, I'm going to divide by the smallest, 0.09760. Something divided by itself is, of course, 1, which is most common to get 1 anhydrate, of course. And then divide 0.96 by 0.09. And we actually get a multiplier of 10. It's a pretty big hydration number, actually. So then the formula in the end would be Na2CO3 attached to 10 water molecules. So it says find the value of X. You could say that X equals 10. We did it. So just to kind of go over it again with the typed out version, the 10.34 grams was what we found in part C, the amount of the anhydrate in the 1 decimeter cubed of water. 105 is the molar mass, so we can get the moles of sodium carbonate. Then if you take the given 27.82 and subtract the anhydrate, you can get the grams of water, converting that to moles. And then you're going to divide by the smallest. So something divided by itself is 1. And the 0.9 divided by 0.09 is 10. So x equals 10. And then our final hydration number plugged in gives us the formula of Na2CO3 attached to 10 water molecules. All right, good job, guys. I hope this helps.